Okay. So the last time we finished was at the effect of boiling and melting point with impurities. So now I'm going to move on to the heating and cooling curves. Okay, so heating and cooling curves are actually graph curves. So basically, we're going to plot all the melting and boiling points on the graph, and that is our heating and cooling curve. So over here, I have the heating and cooling curve, the heating curve for water. So over here, you can see, so this is pure water, okay? This is pure water that I'm talking about. And over here, you can see that water has a freezing point of 0 degrees Celsius, right? So we're heating it up from, let's say, -5. Okay, so this is -5 degrees Celsius, and we heat it up till it reaches 0 degrees Celsius, and that's when it turns from solid to liquid. So at exactly 0 degrees Celsius, it is a mix of solid and liquid. Then moving on, after 0 degrees Celsius, it's liquid, and then you keep heating it up until it reaches 100 degrees Celsius, and that's when it becomes, at exactly 100 degrees Celsius, it starts changing into water vapors, into gas. So at exactly 100 degrees Celsius, it's liquid, it's a mix of liquid and gas. And then moving further, it's water vapor, obviously. So in pure substance, you can see how it is transitioning from one phase to another at a specific temperature. And you can see that for melting, the line is short, but for boiling, it takes a longer time. So this is the temperature. Okay, this is my y-axis, this is my x-axis, and this is the time. Okay, so the time taken for melting to take place is less compared to the time taken for boiling to take place, and that is because in melting, you're just weakening the intermolecular forces. So they were first solid, so they were packed really tight together, and then when they turn into liquid, the forces are just weakening, and so they start slipping and sliding past each other, and then in gas they completely break apart, and we have water vapors. So that's for the pure substance. For the impure substance, we have a graph which does not have a very specific temperature at which there is any phase change. So it happens at a range of temperatures. So let's say this is an impure substance. So this is water and salt, okay? And this is the graph that I plotted. So let's say that uh, we start heating this saline water, and uh, so we're starting at minus like 4 degrees Celsius, and you can see it doesn't start melting at 0. At like 5 it starts melting, and then it goes on, and then when it has completed its melting at 10 degrees Celsius, this is when it's in the liquid phase. Then this is 100 degrees Celsius, so it was supposed to boil off over here, but it didn't. So it started its boiling at 105 degrees Celsius, and it finished at 115 degrees Celsius, and now it's gas. So this happens at a range of temperature. And why this happens is because like if you keep this example in mind, this as it'll start boiling, it will obviously be.
Sundus, sorry for interrupting you. You did the effects of impurities, right, on boiling and melting point. So
Yeah.
ask the students what do they remember from the last class, or what do they already know, how do the impurities affect the boiling and melting point? Can
Yeah.
anybody answer?
No. So
How?
after this explanation, we'll go on to the questions.
No. This is not a question. I want. Yeah, Momina has raised her hand because you have already explained this, so I expect them to know this. Okay, Momina.
Like in the last class, the impurity was salt HCl, so it had huge particles, and so the surface area for maybe like from going to solid to liquid, it had to move fast to weaken the forces of attraction, so the surface area was less.
Yes, very good, because the boiling takes place at the surface, and that surface is occupied by those impurities, so the solvent molecules don't get enough space to leave the surface of liquid and get into the gas, right? So, okay, and what about the freezing point? Does anybody else want to tell the effect of impurities on freezing point? Any other participant wants to explain the effect of impurities on the freezing point? Is Momina the only one? Khizr? What about you, Vara? Okay. Come on. Okay, Khizr? Do you want to explain?
Yes.
Okay. The effect of impurities on the freezing point.
On freezing point.
Yes.
On freezing point, it will take more energy for the water molecules to line up because the impurities will disturb the pattern.
Very good job, but you know, a slight mistake in the wording of your answer, but I do understand that you know the concept, that more energy needs to be extracted, more energy needs to be taken out of it to bring the molecules back to their crystalline arrangement, to their proper arrangement. Good job. Okay, now Sundus, you can continue.
So what I was saying was that the reason why it boils off at a range of temperatures is because if you see this example right here, you can see that it will obviously be the water that's gonna boil off, not the salt. So as the water boils off, so this is happening at a range of temperature. As it's leaving the solution, salt will be left behind. So the composition is like changing every single with every second. The composition is changing. There's always more NaCl than before. So that's why this happens over a range of temperatures. Now I have like some questions so that because this is related to the topic I did before, so I have some questions so that I know you guys still remember what I told you last time. Give the names for the following physical changes. Like, so you guys can raise your hand. Momina, you want to do A?
Yes, so liquid to solid is freezing.
Yes.
Yes, good.
Good
Yes,
job.
good. Okay, now Zainab, ask from Zainab.
Zainab, you want to do part B? Khizr has raised his hand, so I'll unmute him.
Part B, liquid to gas evaporation.
No, they have written at a precise temperature. What does this tell you?
Precise temperature boiling.
Very
Yeah,
good.
this is the last time I told you the difference between boiling and evaporation. So one of the differences was that boiling happens at a specific temperature and evaporation can happen at any temperature. Gas to
Okay.
liquid. See, gas to liquid. Zainab,
Gas to liquid would be condensation.
Yes, good job. And solid to gas directly. So directly is the key word here.
Okay, now
So Vanya, do you want to do that? Fatma?
Vanya, I'm trying to unmute you.
Yes, yes,
Yes, can you do this? Part C.
yes. Sublimation.
Sundus,
Sublimation.
Sundus, please keep your video on.
Yeah, so
Sublimation.
What was that? Can you please repeat?
Sublimation.
Sublimation. Okay, good job. And what was the opposite of sublimation?
decomposition.
Condensation. Condensation.
What was that?
Condensation.
No, no. Who knows the opposite of sublimation? Wadud, 43. Wadud, do you remember?
Decomposition.
No, decomposition is, what is the decomposition, Wadud? Abdul Wadud. Do you remember what decomposition is?
No.
You're breaking down into simpler substances, breaking down into simpler components. Okay, so opposite of sublimation is deposition. Okay, opposite of sublimation is deposition.
Okay.
Okay, move on, Sundus.
So this question we already did it, and now so this is the next question. Sketch a cooling curve for water 80 degrees Celsius to minus 20 degrees Celsius, noting what is taking place in the different regions of the graph. So I'm going to draw the graph, and I want someone to like work it through with me. So Vanya, do you want to do that? Momina?
Can you please repeat the question again?
Okay. So we have to sketch a cooling curve for water 80 degrees Celsius to minus 20 degrees Celsius, noting what is taking place in the different regions of the graph.
So 20 degrees Celsius is the freezing and melting point.
So no,
can you please draw the graph for them?
okay, so this what the question is not saying that this is the melting or the freezing point. It is just giving us a range. So if our minus 20 degrees Celsius is down here and 80 degrees Celsius up here, and we know this is 0 degrees Celsius, so we'll start. So now what this question is saying is that when we lower the temperature for water, so the graph will be this sloping this way, not this way, because if we slope it upwards like this, that means that we are taking it from a lower temperature to a higher temperature. But what the question is saying is, the question is telling us to bring the temperature down from 80 to minus 20. So the slope is going to be this way. So that's why I'm going to start it from here. Okay. So we go all the way down to 0 degrees Celsius. At 0 degrees Celsius, water is freezing, and then down to 20 degrees Celsius. And this is freezing. And this is 80 degrees Celsius, not 100 degrees Celsius. That's why there's no boiling going on. So this is the main sketch of the graph. Okay, so then after this, what do you understand by the term volatile? Momina, you want to do that? Vanya? Okay, Vanya, do you want to do that? What do you understand by the term volatile?
Yes, Vanya, are you having problem with your mic?
Evaporation.
Okay, wait. So, alarm.
Okay. Okay, Noor 29. Noor 29, you want to answer what volatile means? Sundus, what was the question again?
What do you understand by the term volatile?
Okay, Noor. Muhammad Noor Khan, right? Okay. You have a lot of background noise. Okay, Ismail Bari.
Abdul Rahman 22, please don't turn on your video.
Okay,
Again.
yeah, there's zero tolerance for video opening. You know that, right? So yeah, even once will, and I don't want to do that. Okay. So okay, let me. Okay, Ismail Bari. Okay, Ismail Bari, can you please explain what do we mean by volatile?
Assalamualaikum. It means easily evaporated.
So that means in terms
Ethanol.
of boiling point, what does that mean?
The lowest boiling point.
Yeah, the boiling point is very low, lower than, equal to, almost equal to the room temperature, right? So that as at room temperature, it boils.
Yes.
Okay, okay, thanks.
Okay. Now the last question is, put these put these liquids in the order of volatility with the most volatile first. So we're going to look at the boiling point, and the most volatile will be the one with the lowest boiling point, because that its temperature will be reached first. And the least volatile will be the one with the highest boiling point. So who wants to arrange this? Momina? Zainab?
Yeah. The most volatile would be ethanol. Then comes water. And then ethanoic acid.
Ethanoic acid.
Ethanoic acid.
Yeah, so that's the correct answer, because ethanol is 78 degrees Celsius, water is 100 degrees Celsius, and ethanoic acid is 128 degrees Celsius. So this is with the lowest boiling point, this is the highest boiling point. So now once we're done with the questions, I'll move on to the topic that I wanted you to do today, which is types of mixtures. So mixtures could be of two types. Mixture is a mix.
Okay. Before you start the new topic, if there's any question regarding the questions that we have just done, please you can raise your hand and I will unmute you, because the chat box is disabled. If there is any question, raise your hand and we will try to answer. If not, then we will move forward.
Ismail Bari.
Oh, there was.
Yes, Ismail.
I have no question. I don't know why I raised hand.
Oh,
Okay. Okay, Maz, your hand is raised. Please, if you don't have a question, please lower your hand so that we can save time and we can move on. Yes, Maz?
Yes, miss. Could you please explain me the volatility question again? I did not
Yeah,
understand.
were you there in the last class?
No.
Yeah, so we explained volatility in the last class, and volatility is nothing but, ease of evaporation. Okay, Sundus, you go ahead and explain.
so should I continue with this topic?
No, he's asking for the explanation for volatility. So explain it briefly.
Oh, okay. So a volatile substance is any substance which evaporates at a really low temperature and at room temperature. And so it evaporates spontaneously without us, with just absorbing the energy from the surroundings.
So
So,
explain the reason. Explain the reason behind it.
that's because it has weak intermolecular forces. So that's why it just needs a little energy to break them.
See, basically, what is evaporation? Evaporation is when the liquid molecules turn into gas, right? So that is the breaking of the intermolecular forces of attraction, right? Because evaporation is a physical change. In physical change, it is the intermolecular forces that are broken or reformed. Whereas in chemical changes, it is the intra, meaning within the molecule, okay? So because the intermolecular forces are weak of volatile substances, therefore, even the room temperature is enough to break those intermolecular forces. By the word inter, I means between the molecules. So room temperature is enough to break the intermolecular forces, and therefore the liquid molecules go into the gaseous state. Okay. Okay, now move on.
Okay. So a mixture is a mix of any two substances, and a solution is a mixture of a solute which dissolves completely in a solution. So I'll elaborate on these terms later on. But solution is a mixture, but a mixture is not a solution. Okay, so an example of a solution is when you add salt, NaCl, to water. This is a really common solution. And over here, the solute is what we add in the solvent. So solvent gets the solvent allows the solute to dissolve in it. So the solute is something which is dissolved in a solvent, and solvent is something, a substance in which the solute is dissolved. So solvent contains the solute. So now the mixture. So coming back to the mixture, there are two substances which are just mixed together. So there is no difference in their chemical consistency, chemical form. They are just put together. They're just mixed together. So for example, iron and sulfur. So this is not a reaction. This is just mixing. Okay, we can still separate them, but so if they're in a powdered form, and if they're not, like if they're mixed up really well, we can only separate them using a difference in their physical properties. So if we make a list of all their physical properties, we can then differentiate between them. So uh, iron is solid, sulfur is solid, and that is same, so we're not going to use that. Iron is gray, sulfur is yellow, but color would be really difficult to use in separating, because you can't really pick out all the iron, the gray particles and the yellow particles, so that's not useful to us either. Iron is attracted to magnets, sulfur is not attracted to magnets, so we can still think about that. Melting point is 1538 degrees Celsius, and sulfur's melting point is 115.2 degrees Celsius. So they are crazy high. So they're really really hot. So we need really high temperatures for both melting and boiling. So we can't use any of those. So we're just going to use this physical difference, which is that iron is attracted to magnets and sulfur is not. So let's say that this is our mixture of iron and sulfur, and using the magnetic property, we bring a magnet close to it, and the iron gets attracted to the magnet. So they're all going to be stuck to the uh, magnet this way, and then when we remove the magnet, we can brush off all the iron filings, the iron powder, and sulfur is what is left behind. So so I hope like you guys know what that mixture is, just like two substances mixed together. So I want to ask to test you guys by asking this question. Okay, so you guys.
Okay. Okay, I'm sorry for interrupting again. I just want to add one point that remember, solution is a type of mixture. You guys have not done types of mixtures. There are different types of mixtures. Solution is one of them. Then we have suspension. Then we have other as well. But you know, it's not included. Yeah, it's not included. But yeah, solution is one type of mixture. Okay, and yes, yeah, and Sundus very beautifully explained that when we are separating substances from a mixture, remember that we make use of the difference in the physical properties. Okay, we make use of the difference in their physical properties. So I like the way Sundus has enlisted the physical properties that she's using. Okay, and so the difference in color was not useful, and the boiling and the melting point were expensive. I mean, they are, you know, you will need electricity or you will need heat energy to bring that, to bring these substances to their melting and boiling points, right? So it is economically more suitable to use this difference in the attraction towards magnet, right, Sundus?
Yes.
Yes. Okay. Now you can move on.
So my question is, in which pair of substances is each substance a mixture? So Momina, no, Abdul Rahman, do you want to answer? So I'm trying to unmute you.
Air is mixture.
Okay, so air is mixture. So in all these options, we have air here and here. But the question is asking which pair of substances are both mixtures. So is water a mixture or is seawater a mixture? Abdul Rahman?
Seawater is mixed.
Yeah, so the answer is D, because air is a mixture, but water is H2O. So that's an element. Lime water is calcium oxide, I guess. I'm not really sure, but this is H2O. So they both are compounds and they're made of one substance each. Same goes for this. This is also a compound of calcium, and this is also a compound of calcium, but these two are mixtures. So moving on to solutions.
No, wait. Ask them, why isn't a compound a mixture? What's the difference between a compound and a mixture? Who will explain?
Zainab, do you want
Zainab?
Yes, in a compound, the elements are chemically bonded with each other. And in a mixture, they aren't chemically bonded, and they can be separated by the help of their physical properties.
Very good. And then there are, yes, and the two substances in a mixture have inter. I'm emphasizing on the word inter, I-N-T-E-R, intermolecular forces. Whereas in a compound, they have intra, meaning within the molecule, I-N-T-R-A. Forces of attraction, right? And another difference I would like to add is that in a compound, just as Zainab said, that the compounds are chemically bonded together in a specific ratio. Like, for example, Sundus just wrote down the formula for lime water as calcium oxide. So each molecule, or each particle is composed of one atom of calcium and one atom of oxygen. So we have a ratio of 1:1. Calcium, for each calcium atom, you have one oxygen atom, and vice versa. Same goes for quicklime. Okay, I don't remember. Maybe quicklime is maybe calcium hydroxide or something. I forgot. Or maybe it's calcium carbonate. Okay, so but some calcium compound, right? So again, we have a specific ratio. Okay, we have a specific ratio. So what are the two differences between the mixture and the compound? is that the elements are chemically bonded in a compound and also in a specific ratio, whereas in a mixture, they just have intermolecular forces in between them. We have just, placed them together. They might develop intermolecular forces if they are soluble with each other. And then they are not in any specific ratio. Okay, so these are the two differences. So that is why we will not call lime water or quicklime as mixtures, but they are compounds. Good job, Sundus. Okay, move on.
Okay, so moving on to solutions. In a solution, the chemical form of a substance is altered, and if it's not altered completely, like in a salt solution, salt is still salt. If not completely, it's always to some extent, and I'll elaborate on that. And if I give you like a simple explanation, it's the fact that you know how like in if you have a beaker of water and you add salt in it, in the water it's going to break up into sodium cations and chlorine anions, right? So this is it's chemically altered. So in solution, the chemical form of a substance is altered, if not completely, always to some extent. So these are the differences between mixtures and solutions. Mixtures keep their properties. Solutions are a special kind of mixture. So their chemical form is altered a bit. Do not form new properties. Mixtures do not have new properties, but solutions do have substances with new physical properties. Mixtures can be separated. Solutions can be separated by different, and I should say difficult techniques. So some way could be we can separate mixtures by hands, sifting, filters, magnetism. Okay, the similarities between both of them are they both contain two or more substances. Both of them can be found everywhere, and they both are mixtures. So continuing on solution. Solution has a solute and a solvent. So solid dissolving in a liquid. Okay, so this solute is always solid, at least as far as I know. When liquids and liquids are mixed together, they both are called miscible liquids. So this is NaCl plus water, which is a very common example. Miscible liquids is so this is one type of solution. The other type of solution could contain miscible liquids, which are two soluble liquids. An example is ethanol plus water. And alloys are a solid solution, type of like a solid solution. And I know that sounds really weird, but if you really look at it, it is a solution, sort of. So if we look at steel, okay, so it has carbon, iron, and chromium. Okay, so which are the main elements? There are many more. So this is what carbon looks like, iron and chromium, when they are separated. And when they are mixed together to form steel alloy, so they are not reacting or anything. This is just a solution. Okay, you can see how they're mixed up really nicely, but steel has different properties, like it doesn't rust and iron does. So you can see how it changed. So magnesium is another substance in steel. Okay, and this is how it's a solution. And moving on, moving back to mixtures, a solid mixture, I already gave you an example, iron and sulfur, and I told you how to separate it and everything. A liquid mixture, which would be solid and liquid, so it's not dissolving completely. Dissolving is like when the solute, it actually gets space between the particles of um, the solute actually gets space between the particles of the solvent. That's when it's dissolved. But in suspension, they're kind of just suspended over there, just like hung in the middle. And if you let a suspension stay still, it'll the product is going to like settle down at the bottom, like sand and water. So you can have muddy water, which is suspension, and if you let it stay, sand will settle to the bottom. Okay, and then another sort of mixing of substances is the immiscible substances. So water and oil are immiscible. That is, they have a distinct line of separation. Okay, so this is not a solution or a mixture, and I searched on this a lot. I tried to figure out if this was a solution or a mixture, but I couldn't really figure out. So I just want to how should I show this? Okay, just give me a second. I'll be right back.
Sundus, no, you can just keep it there. Keep it there, tilt it a little, and they'll be able to see it. Tilt it a little, and they'll be able to see it. It's okay.
No, actually, then the oil floats up to the other side. So wait, I have a better idea. I'm just coming.
Okay, so I want to ask you. So Sundus is discussing the different types of mixtures with us. Okay. So can anybody tell me, in terms of the intermolecular forces, what is the difference between a solution and a suspension? In terms of intermolecular forces, what is the difference between solution and suspension? And another thing, I don't know if I showed you an animated video that is showing a solute dissolving in a liquid. If I haven't shown, I'll show you in the next class, okay? Or maybe I can show you right now. Okay, let me see. So Sundus is trying to show us a suspension. Isn't it a suspension? Yeah. Now, because oil is less dense and it does not dissolve with water, it forms a layer at the top of water, okay? Here, okay? So you can see, and you can make it yourself. You know, she has just put in water and then she has added oil into it. But because oil does not dissolve in water and it is less dense, therefore it forms a layer at the top of water, right? Okay, so why doesn't the oil dissolve in water? Okay, Zainab. Yeah, please, others also participate. I want everybody to participate. Okay, Zainab?
Yes, I'm not so sure. Does it have anything to do with its boiling point?
No. Zainab, are you in grade 8?
I'm going to. Yeah.
Okay. Okay. So no. You see, that's exactly why I asked you the first question. What is the difference in terms of intermolecular forces between a solution and a suspension? What I'm trying to ask is, what is the difference in terms of intermolecular forces when the solute is dissolving, or when a solute is soluble in a solvent, and when a solute is not soluble in a solvent? Okay. Yes, Momina, are you?
I will try. I'm not sure if my answer is correct. Maybe because the intermolecular forces are too strong that they do not allow any other types of molecule to get into them. Like if, for example, we dissolve sugar into water, the intermolecular forces are weak, so they allow water to get in. But maybe the intermolecular forces are too strong in the oil that they do not let the water to get in.
Okay. Okay, you know what? Yes, I think, yeah, you are partially correct. The thing is, look at it this way. You know, in a solution ka matlab kya? When the solute is dissolving in the solvent, okay? Basically, the solute and solvent are good friends. So, you know, like how some people make friends easily and others cannot make friends easily. Like, for example, if you have a newcomer in your class, it will take some time for that newcomer to become friends, right? Now, if that newcomer is just like others, you know, others feel friendly, so they will make friends. I mean, they will develop friendship with her, and so that's how she will mingle up with the class fellows, and so that's like solute dissolving. So when the solute forms intermolecular forces of attraction, meaning that the solvent molecules are attracting the solute, that is when we say that the solute has dissolved. Okay. Now, when a person who is not friendly, or maybe he is different from the others, and the others think that, you know, he is different from us, and so they don't feel friendly towards her, and so that person will not make, you know, friendship with the others, and so he has not, that solute has not dissolved. So think of it that way. So oil and water, they don't get along. इनकी बनती नहीं है आपस में. Okay, oil and water, they don't get along. Now you might ask why, right? Now that has to do with the structure of the molecule. Okay, I will talk in detail about the structure of the molecule. Water is polar, meaning, you know, like if you look at the structure of water, it has oxygen and it has hydrogen atoms, right? So oxygen is more electronegative. Now you guys are entering into grade 8. I expect you to know the meanings of electronegative. I expect you to know the meanings of polar molecules. You should know what a polar molecule is. And if you don't know, then that means you need to revise your grade 6 and 7 chemistry. And that is why I encourage most of the students to please attend my grade 6 classes as well, because I have seen that many of the students have their basics very weak. Okay, so because water is a polar molecule, it has attraction towards polar substances. And because oil is non-polar, now you should know the meanings of polar and non-polar. If the oil, because the oil is non-polar, it does not get along with the polar water molecules. Okay. So that is what we mean by solution and suspension. So in suspension, no forces of attraction have developed between the solvent and the solute, whereas in solution, there is a force of attraction between the water and the oil. I mean, between the solvent and the solute. Okay. Okay, Sundus, move on.
Yeah. Okay. So immiscible substances don't get along with each other, and this is not a mixture nor a solution. And you can think of it as a mixture because there are two things put together, but I searched the net for this and it doesn't put it into solution or mixture category. Now, moving on to suspension, which is another sort of mixture. A suspension is a mixture containing large particles that will settle on standing. So you can think of sand, and over here, when you let it sit, so this is when you don't let it sit, and this is also how the water is on the roads, because you know the wheels of cars and motorcycles just like disturb the water again and again, so this the sand is always suspended, and that's why the water looks muddy. But if you let it stand, it settles right onto the base of the container, so due to the action of gravity, and you can see that it's settled.
Also talk about the density, because sand is denser than water and therefore it settles down. It's heavier than water, so basically, so it settles down. If there's any substance which is less dense than water, then of course it won't settle at the bottom, but rather it will flow at the top.
Yeah.
So the reason why we have suspension at the bottom diagram of that Sundus has drawn is because it is being stirred. It is being stirred. So basically we are mechanically forcing the sand particles to be in between the water particles. But remember, sand does not dissolve in water, no matter what you do.
So it's just suspended in between, just like
even if you heat, even if you keep stirring it, it will never ever dissolve in water. It has zero solubility in water. Okay, move on.
So we can separate them in two different ways. So the first way, so this is an insoluble solid from liquid. So first of all, we're going to discuss how we can separate insoluble solids from liquids. So now I'm using the same example, the sand and water. So for this way, so first let me discuss decantation. So for this, you have to wait for it to settle. Okay, so when everything is settled, we can then tilt the beaker slowly. So because sand is denser than water, it will stay to the bottom of the beaker and the water will flow out. And so we can just get it in another beaker like this. But the setback of this way is that you need a lot of time. You have to leave it untouched for like an hour or so, and you need space. You need some place to keep it untouched. So our alternative for this is filtration. So for filtration, you can just go ahead and put the suspension in. So I put the suspension in. This is the filter paper. Okay.
Okay, so Sundus, what is the physical property that we are using in filtration? What is the physical property difference that we are using in filtration?
We're using the difference in the size of the particles.
Good job. Yes. And remember, the solute will settle mostly it is the solute that will settle in decantation. I'm talking about decantation. In decantation, it is the solute that will settle if it is denser. Okay. And the solvent will flow out. Okay, what if the solute is less dense than water? If it is less than water, then it will form a layer at the top, right? Then how can we separate?
So you could either filter it or take it out like using a spatula or something.
Nuh-uh.
I'm not really sure.
Then again, we can use decantation, but in that case, it will be the solute coming out because it's at the top, right?
No,
Whatever.
wait, I think we can use a separating funnel, so the one with the tap at the bottom.
Yeah, or we can use a burette. We can use a burette. Okay, we can use a burette, and so you know, I wish I could show you the burette, and so you know, we can let the denser solvent flow out, and we will be left behind with the less dense solute, right?
Yeah.
Or we can just simply use decantation as well. Okay, but we will have the insoluble, less dense solute at the top, and that will flow out, and solvent will be left behind. Right. Okay.
So what actually happens in a filter paper, so the filter paper's job is that if you imagine that these blue circles are the sand and the green tiny dots are the water, you can see that the pores in this membrane or this filter paper are enough for the water to pass through, but they are not enough for the sand to pass through. The sand is too big to pass through the pore. So the sand will like remain behind and you will get the water without sand. So over here I've labeled the apparatus we need to use for this. This is a filter paper. This is the funnel or the filter funnel. This is the residue. So the solute, this is the sand that was in our solvent, which was water, which is the filtrate after getting filtered. This is our beaker. So this is one way to remove it, but we're still not done with the different types of ways we can take out the solute if it's a suspension. So one was decantation, the other was filtration, and there is yet another that they use in biological labs to test blood. So over here, the solute is the RBCs, and the process is centrifugation, and we use a centrifuge machine. So this is what a centrifuge machine looks like, and over here you can put the test tubes. So the test tubes go right there, and they have blood, and it moves the test tubes around really fast, so much so that the RBCs settle to the bottom. So how this happens is, so this is a diagram, okay, that I made. So imagine that this is the axis and this is, there's a rope, and it is attached to the test tube, okay? Now it's containing blood. And even though I know you guys have not done centripetal force, but it's a force that acts outwards from the center when something moves in circular motion. So because of the centripetal force, this forces the denser objects, the RBCs, to settle at the bottom, and the plasma and the white blood cells and platelets and everything goes up. And the white blood cells they do form a film right here with a white film because they are still cells. So this is all plasma, platelets, and broken cells. So the less dense moves towards the center and the more dense settles down. So a centripetal force is away from the center, so denser things like RBCs settle down and less dense objects float up, and that's why they form these nape layers.
So Sundus, correct me if I'm wrong, that these less dense substances are following the centripetal force, right? The centripetal force is succeeding in moving the less dense particles in its direction.
Particles.
Yes, so because the less dense particles are lighter, and therefore the centripetal force is, like sort of pulling them, towards the surface. Okay, we have a couple of hands raised, so I would like you to answer their questions.
Okay.
Abdul Wadud. Yes, Abdul Wadud?
Yes. So how can if we use the centripetal force to move to remove the red blood cells? So how can we take out the red blood cells when the up there's plasma and everything?
Okay, so you're asking why, how we can remove the plasma red blood cells afterwards.
Okay,
then.
okay, so
Yes.
1 minute. Do you guys know the composition of blood? You don't know, right? I'm sure that you guys have not done blood, the composition of blood. So basically, blood has red blood cells and has white blood cells. Okay, Abdul Wadud, please mute yourself. Oh, sorry. Okay. So, so the blood is composed of the heavier red blood cells and then lighter white blood cells, and then all these cells are suspended. Okay, I'm using the word suspended. They are suspended in water solution, in a water solvent, and that water solvent is plasma. Okay, it is predominantly water, right? So because red blood cells are complete cells, so they are relatively heavier. Okay, you don't have to go into the details of the blood composition for now for this class, but just appreciate that the lighter substances are moved towards the centripetal force or by the centripetal force, and the denser, heavier particles are left behind. That's all. Okay, don't get confused. Blood has two components, heavier and less dense, heavier and lighter. The lighter ones are pulled by the centripetal force and the heavier ones are left behind. That's all. Okay, so again, we are making use of a physical property, which is the difference in the particle weight. Okay, so Sundus, please turn your video on. Keep your video on.
So
okay?
It's on. It's on.
Yeah.
Can you
Okay,
see
okay. Yeah, okay. So I hope you got the point. You don't need to get into the details of it for now. Okay, Ismail Bari, is there a question you want to ask?
Yes, I'm confused in why is lime water and water not a mixture, but salt water and water is.
Okay, good, good. Okay, Sundus, only 4 minutes are left, so let's answer their questions, okay?
Okay.
Okay, so can you answer his question? He's asking that he's confused that why are lime water and quicklime compounds? They are compounds, and why is, what was the other thing? The other thing, the seawater is a mixture.
Yeah. So this is their name, I guess.
Yeah, they're using their common names to trick you. Okay, they're using lime water, quicklime. If they had used the formula If they had used the formula, then it would be easier for you to understand. Okay?
Yeah, so these are just the names, and the formulas are different. There's this like calcium compound, but for water,
Just write down the formula for lime water. I think it's calcium hydroxide. So go ahead and write down the formula of calcium hydroxide. Okay. And quicklime is calcium oxide. Okay. And then lime water is okay. Lime water. So can you see is yeah, it's calcium hydroxide. Okay. So can you see that they are the elements are combined together in a fixed ratio, and so they are one substance. They are one substance. Do you understand? So a substance meaning that they have only one type of molecule. Okay, buddy. Ismail. They have one type of particle. And what is that particle? That is calcium oxide in quicklime. In case of quicklime, the particle is calcium oxide. In case of lime water, the particle is calcium hydroxide. Do you understand? And in a mixture, for example, seawater, we have two types of particles. Sundus, seawater is made up of sodium chloride and water. So what are the two types of particles that we have in seawater? Sodium chloride and water. So when you have more than one type of small particle, if a thing is made up of more than one type of particle, that is a mixture. And if you have this only one type of particle, that is a pure substance. Did you understand, Bari? I'm unmuting you.
That was not my question.
Okay. What was the question?
Because why is lime water and water not a mixture, but seawater and water is?
So I just answered it. What
No,
did you understand?
You answered why is lime water and quicklime not a mixture?
Okay, tell me, what do you understand by mixture?
Yeah, I get his question. He's saying why the answer was not B and it's D. The question is asking in which pair of substances in each, which of these two are both mixtures. So air is a mixture, water is a compound. Lime water is a compound, water is also a compound. Quicklime is a compound, lime water is also a compound. Seawater is a mixture, air is also a mixture. So that's why the answer is D. Did I answer your question?
Okay, Bari, are you satisfied now? I'm unmuting you. Please answer me. It's okay.
Yes, thank you.
Did you understand?
Yes, thank you very much.
Okay, can I ask you a question now? I want to ask you. Okay, tell me, what do you understand by mixture?
Mixture is the mixture of more than one substance.
More than one substance? So how do you decide that it is made up of more than one substance?
Like a pure substance like water and seawater.
When you have different types of particles, right?
Yes.
Yes. So I want you to say that. A mixture is made, yeah, you have to say that. A mixture is made up of different types of particles.
A mixture is made up of different type of particles.
Yes. The reason why I'm asking you to pay attention to these words, because these are key words, okay? If you are asked to, you know, write it in the form of an answer, these are the key words, okay?
Yes.
Mixture is made up of different types of particles, and they can even give you, and there's a very good question in grade 6 chemistry for you book at the end of, you know, first chapter or the second chapter, where they have given you different pictures, and they have made the particles with different colors and different shapes. So when you see a container with particles of different shapes, that means that they are different particles, and so that's a mixture. And if you see the same type of particle, that's a pure substance. Okay? So I don't know if you remember that question.
Okay,
Okay,
so a
another
mixture
thing.
is
Yes,
different,
made up of
made
more
up
than
of
one
different,
type of
more than
particle.
one type of. Okay, thank
You
you.
get that?
Yes.
Okay, good job. Okay. Yes, Momina, you have an answer. You have a question?
No, sorry, my hand was left raised. You asked about the composition of blood, so at that time I was going to answer.
Okay, so please go ahead and tell me, Momina, which grade are you?
I have been promoted to grade 7.
You have been promoted to grade 7,
Yes.
but I also see you in my grade 9 classes. You're
Yes.
taking my grade 9.
Yes, I just like to attend.
Good
And
job. So are they helping you out?
yes.
Yes, I like it. And I also like your participation. And I encourage people to attend all my classes because, you know, if you ask me from grade 6 onwards, all the topics are the same. All the topics are the same. They're just, you know, dividing. They have just divided, but the topics are the same. Okay, so Momina, can you share the composition of blood with everybody?
Yes. So
Yes,
is made up like she just told the way to separate blood. So the first part I would say plasma. Plasma is
yes.
a yellow liquid. It contains food which are like sugars, amino acids, vitamins, and minerals.
Yeah,
It
basically it is water solution. Okay, it is predominantly made up of water, and then it has these things dissolved into it, like salt and water and carbon dioxide and, you know, nutrients and minerals.
and
Yes,
has blood proteins like antibodies. It has chemical wastes like urea. It has
very good.
hormones. And
Very
then there are the red blood cells, the white blood cells, which are of two of types, lymphocytes and phagocytes, and then platelets. Platelets are tiny bits of dead cells.
right, right. And then we have the red blood cells because they are complete cells, so they are the heaviest. They are the
Yes,
heaviest part.
yes.
Right, right. And yeah, okay. Jazakallahu khairan. Good job. So, okay, so we won't go into the details of centrifugation, but just appreciate that the centripetal force, which is acting from the center of the circle outwards, causes the less dense particles to move out or to move at the towards the top of the test tube. Okay, okay, then inshallah we will continue from here in the next class. But just a little question, one question that I want to ask. Oh, sorry. Okay, sorry about that. Okay, this page number 25, page number 25, okay? I want you to pay attention to this figure 2.7. The apparatus for measuring the melting point of a solid. A water bath can be used for melting points below 100 degrees Celsius and an oil bath for those above 100 degrees Celsius. So my question is, why? Why are we using a water bath for measuring the boiling point for this solid? Okay, this is investigating heating and cooling curves. So why for investigating the melting point I mean, the melting point which is below 100 degrees Celsius, why are we using a water bath? And for melting points above 100 degrees Celsius, are we using oil bath? Can anybody answer?
Can I
Aisha? Yes, yes, Ismail? Yes? Yes,
Because in water, the substance you're trying to measure the boiling point will evaporate first,
yes, very good.
and in
So
the
the,
oil,
yeah, so,
oil will evaporate first, and the substance will be left behind.
right. Meaning the water will evaporate before the melting point of the substance is reached. Right.
Yes.
And what about the oil bath? So
Oil
why? Yes.
oil will be evaporated, and the substance that no, I don't know for oil. I know for water. I'm not sure for
Yeah. So
oil.
yeah. So you use the same concept for oil bath as well. Some of the oils have a boiling point greater than 100 degrees Celsius. So if the solid that you're trying to test has a melting point above 100 degrees Celsius, so we can easily use that oil which has boiling point above, way above 100 degrees Celsius, so that the oil does not evaporate before the solid.
Yes.
Yeah, so that the oil does not evaporate before the solid, because if the oil will start evaporating, it will cool down because evaporation has cooling effect, if you remember. And so
Yes.
the melting point of the solid will not be achieved, or or readings of thermometer will not be accurate, right?
Yes.
Okay. So I was thinking of increasing the time for my class to maybe 1.5 hour or 1 hour 15 minutes or so, because I won't be able to take as frequent classes. But whatever I decide, I will decide on the schedule and I will post in the group. Okay. Sundus, so let's wrap off. Let's end this meeting. Okay.
Yeah, sure.
Okay then. Okay. Assalamu alaikum wa rahmatullahi wa barakatuh.
Allah Hafiz.